You know when you're mixing sugar into your tea or maybe some salt into a soup, it seems so simple, right? But it turns out there's some really cool science hiding behind that simple little stir. So today, we're going to pull back the curtain and take a look at the magic of mixing.
Oh yeah, we have all been here. You're trying to get that drink just right, you add one more little spoonful of sugar and nothing. It just sits there at the bottom, kind of looking at you, refusing to disappear no matter how hard you stir.
So what gives? Why does that last spoonful just seem to give up? It's like the water is just full. Well, that's the exact mystery we're going to solve today.
Okay, to really get what's going on, we need to start with the basics. We have to figure out what we're even making when we mix these things together. So, first question, what exactly is a solution?
Well, a solution is just what scientists call a uniform mixture. And that sounds fancy, but think about a really good glass of lemonade. Every single sip tastes exactly the same, right? That's because all those little sugar and lemon particles are spread out perfectly and evenly among the water particles, just like you see here. Nothing is clumped up, it's all one smooth mix.
All right, if we're going to talk about this process, we need to know the lingo. There are three key players, three main terms that unlock this whole thing, and they're actually pretty simple.
First up, you've got the solute. That's the stuff that's getting dissolved, like our sugar or salt. Then you have the thing that's doing the dissolving. That's called the solvent. And in so many things we see every day, our go-to solvent is just good old water.
And it all comes together in this beautiful, simple little equation. You take a solute, you add it to a solvent, and bam, you get a solution. It's the basic recipe for everything from your morning coffee to the oceans themselves. Now here's a fun little curveball that seems to break all the rules. In the super sweet syrup for gulab jamun, there's actually more sugar, that's our solute, than there is water, the solvent. So why on earth is water still the solvent? Because it's the one providing the liquid environment for everything to happen in. Its job is to be the stage where the sugar can break down and mix. It's a fantastic little example of how these definitions work.
Okay, so this brings us right back to our original problem. If a solvent's job is to dissolve stuff, can it get overworked? Is there a limit? Can it actually get full? Let's find out. I mean, really, where is the line? At what point does the solvent just throw up its hands and say, nope, I'm done, no more room? Let's just picture this, right? You take a glass of water, you dump in 1 spoonful of salt, give it a stir, and poof, it's gone. The second one, same thing. But if you keep going, 3 spoons, 4, eventually you're gonna hit a wall. And that salt is just gonna start piling up at the bottom. The water has done all it can.
And that moment, that I'm full point, has a scientific name. It's called a saturated solution. It means that the liquid is holding the absolute maximum amount of solute it possibly can, at least at that specific temperature. That extra sugar at the bottom of your drink, yep, you were looking at a saturated solution.
But wait, what if you really, really want to dissolve that extra sugar? Is there a cheat code? Well, turns out there is. And the secret is all about changing one simple thing. The temperature.
For most solid things, like our sugar and salt, the rule is pretty easy. Turn up the heat. A hot solvent just has more energy. Its little particles are zipping around like crazy, making more room to dissolve more stuff. And that's exactly why it's a piece of cake to dissolve sugar in hot tea, but it's a real struggle in a cold glass of iced tea. Okay, but get this, and this is where it gets really wild. When you're talking about dissolving a gas into a liquid like water, the rule gets flipped completely on its head. For gases, colder is actually better. And this isn't just some random science fact for a trivia night, This is absolutely critical for life on our planet. Cold water holds on to more dissolved oxygen, which is literally what fish and aquatic plants need to breathe. But as the water warms up, that precious oxygen just escapes back into the air. This has a huge direct impact on the health of entire underwater ecosystems. So we've pretty much cracked the case on dissolving. But what about all the things that don't dissolve? Why do they just float or sink? Well, this leads us to our next big idea, which is a property called density. And fun fact, when you dissolve salt in water, the new saltwater solution is actually denser than it was before. I mean, just look at this. You've got sand, which sinks like a rock, and then you've got sawdust, which just bobs around on the top. It's the same liquid, water, but you get 2 totally different outcomes. So what's going on here?
The answer, my friends, is density. And the easiest way to think about density is just how much stuff, or mass, is packed into a certain amount of space.
Imagine a bus at rush hour, totally crammed with people. That's high density. Now picture that same bus on a Sunday morning with just a few riders. That's low density. And the math behind it is actually super straightforward. You just take the mass of something, how much stuff is in it, and you divide that by its volume, which is just the space it takes up. That simple little calculation tells you its density.
This quote from our source material just hits the nail on the head. When we say something like iron feels heavier than a piece of wood that's the same size, what our brains are really picking up on is the difference in their density. The iron just packs way more stuff into the same amount of space.
So there you have it. From dissolving sugar in your coffee to watching a log float down a river, the science of solutions and density is literally all around us. So the next time you see something dissolve, or sink, or float, you'll know exactly what's going on under the surface. My question for you is, what are you going to look at a little bit differently